Image enhancement in frequency domain. In this lecture, we will learn about introduction to the basic properties of Fourier, preliminary concepts of complex number, Fourier series, impulse and Fourier transform, convolution, sampling and Fourier transform of sample function, discrete Fourier transform of one variable. What is frequency? It is the number of times that a periodic function repeats the same sequence of values during a unit variation of the independent variable. What is a filter? It is a device or material used for suppressing or minimizing waves or oscillations of certain frequencies. In the following discussion, we will focus on how Fourier transform and the frequency domain can be used for image filtering, connection between image characteristic and the mathematical tools used to represent them, impact of Fourier transform on the images. A brief history of Fourier series and transform is given. The French mathematician Jean-Baptiste Joseph Fourier, born in 1768, is most remembered for his book The Analytic Theory of Heat. Basically, Fourier's contribution in this field states that any periodic function can be expressed as the sum of sines or cosines of different frequencies, each multiplied by a different coefficient. It does not matter how complicated the function is. If it is periodic and satisfies some mild mathematical conditions, it can be represented by such a sum. Even the functions that are not periodic but whose area is finite can be expressed as the integral of sines or cosines multiplied by a weighing function. The formulation in this case is called the Fourier transform. The function expressed in either a Fourier series or transform can be reconstructed completely via an inverse process with no loss of information. One of the most important characteristics of these representation is that it allows us to work in Fourier domain and then return to the original domain of the function without losing any information. We can understand the importance of Fourier series through the given example. Focus your attention on figure E. Can you write this function in mathematical form? The answer is maybe, but it will be a very difficult problem. This function can be easily written as the sum of the sine and cosine functions of the above four figures. Some of the properties of Fourier transform and their proof are given below. The linearity property, time shifting property, time differentiation property, time integration property, frequency shifting property, and time scaling property. The frequency shifting property and time scaling properties are of great importance. According to the frequency shifting property, multiplication of a function ft by exponent of j omega t is equivalent to shifting its Fourier transform f omega in the positive direction by an amount omega. This theorem is also known as frequency translation theorem. The time scaling property states that compression of a function in time domain by a factor b is equivalent to expansion of its frequency domain by the same factor or vice versa. Some of the basic concepts that are used later in this chapter are briefly discussed below. Complex number. A complex number C is defined as C is equal to R plus Ij, where R is equal to real number and I is equal to imaginary part of the number. The conjugate of C is equal to r minus ij. Complex number can be viewed geometrically as a point in a plane whose abscissa is real axis and whose ordinate is the imaginary axis. Complex number in polar coordinates can be written as mod of c multiplied by cos of a plus j sin a. Let us assume that a complex number a plus bi is given. Then it can be represented on the complex plane as given in the figure. Fourier series. A function ft of a continuous variable t that is periodic with period capital T can be expressed as the sum of sines and cosines multiplied by appropriate coefficients. This sum is known as Fourier series, has the form as given. An impulse may be viewed as a spike of infinite amplitude and zero duration having a unit area. A unit impulse of a continuous variable t located at t is equal to 0 is denoted by del t and is defined as given. It is also constrained to satisfy the identity that integration of del t over minus infinite to plus infinite is equal to 1. Impulse function has shifting property, which is very used in determining the value of any function at a given time t0. If x is represented in discrete variable, then del t is denoted as given. And this definition should also satisfy the summation of x from minus infinite to infinite of del x should be equal to 1. The shifting property for discrete variable has the same form as in the continuous variable. Impulse train. An impulse train can be defined as the summation of impulses that are placed at delta t units apart. The importance of impulse train can be understood later in this chapter. The Fourier transform of a continuous function ft of a continuous variable t is given, where mu is the frequency. Conversely, if f of mu is given, we can obtain f of t back by using the inverse Fourier transform as given. The above two equations comprise the so-called Fourier transform pair. Using the Euler's formula, we can also express it as shown. Fourier transform is an expansion of f of t multiplied by sinusoidal terms whose frequencies are determined by the values of mu. Because the only variable left after integration is frequency, we say that domain of Fourier transform is the frequency domain. Let us obtain the Fourier transform of a gate function. From this example, we get that the Fourier transform of a gate function is a sampling function. The transform of this function, which is band limited, extends to minus infinite to plus infinite. Its spectrum is nothing but the mod of its Fourier transform. In general, the Fourier transform contains complex terms, and it is customary for display purposes to work with the magnitude of the transform, which is called the Fourier spectrum of frequency spectrum. Now let us determine the Fourier transform of an impulse train. The impulse train is periodic with period delta t, so it can be expressed as Fourier series as given. We see that the integral in the interval minus delta t by 2 to plus delta t by 2 encompasses only the impulse that is located at the origin. Thus, preceding equation becomes as shown, and the value of coefficient Cn becomes 1 upon delta t. The Fourier transform of this train function is shown. This result tells us that the Fourier transform of an impulse train with the period delta t is also an impulse train whose period is 1 upon delta t. Convolution. Mathematically, a convolution is defined as the integral over all the space of one function at x times another function at u minus x. The integration is taken over the variable x, typically from minus infinity to plus infinity over all the dimensions. So, the convolution is a function of a new variable u, as shown in the following equations. The cross in a circle is used to indicate the convolution operation. The mathematical representation of convolution is as shown. Now suppose we have a filter of width 3 in 1D. If x is the pixel of our interest, which is the position in the signal and the center of the filter, through the visualization we can understand how the convolution operates. The multiplication between the filter coefficients and the input signal is shown. 1 multiplied by 2 plus 2 multiplied by 1 plus 1 multiplied by 1 is equal to 5. This is the filter response. This response is then divided by 4, which is the weight of the filter, 1 plus 2 plus 1. Similarly, we get the rest of the values as 7 by 4, 7 by 4, 5 by 4, 5 by 4, 7 by 4, 7 by 4, 5 by 4. This process is called convolution. Correlation may be defined as the degree of relationship between any two or more quantities in which they vary together over a period. Its visualization is given as below. Again we use a filter with filter coefficients 1, 2 and 1. The normalized filter response is 5 divided by 4. The difference between convolution and correlation is that convolution is an integral that expresses the amount of overlap of one function as it is shifted over the another, whereas correlation is used to compare the similarity of two sets of data. The correlation result reaches its maximum value at the given time when the two signals match the best. This property of correlation is often used in the identification of an object in image. In image processing, we use correlation, but always call it convolution. If the filter used is symmetric, then correlation is equal to convolution. Now let us apply convolution on images. We have a 2D filter as shown whose equivalent weight is 9. We have an image of 5 cross 5. The process of convolution in 2D is same as in 1D. We put the filter on the image and sweep it across it. The output of the first is given as 12 divided by 9. It is slowly swept from column to column and then from row to row. The output image can be seen as 3 cross 3 image. The mathematical formulation of 2D convolution and correlation is shown. In 2D also, If a filter is symmetric, then correlation is equal to convolution. Let us convolute a function f over h. Let it be equal to g of x. Then it can be written as integration of f of tau multiplied by h of x minus tau into d tau from minus infinite to plus infinite, the output of which is shown. Through this example of convolution, we can understand the mechanics of convolution. Steps to perform convolution are: reverse the function h of tau in time yielding h of minus tau. Shift h of tau by an amount t giving h of t minus tau. Multiply the shifted h of t minus tau by s of tau, obtaining s of tau multiplied by h of t minus tau. Integrate this function to find the area under the product to obtain the value of the convolution at the single time t. Complete the steps 1 to 4 for all minus to plus values of t where overlap of the function occurs from minus infinity to plus infinity if necessary. The Fourier transform of a convolution of two functions in time domain results in product of those functions in frequency domain as shown. Thus, in other words, we can say that f of t convoluted with h of t and h of u multiplied by f of u are the Fourier transform pairs. Following similar development, we would result in the other half of the convolution theorem, that is, in time domain, f of t multiplied by h of t its transform is the convolution of h of u over f of u. Convolution theorem is the foundation for filtering in the frequency domain. Some of the properties of convolution are shown. Convolution is commutative, associative, and the cascaded system is also shown over here. Some of the applications of convolution or correlation are object detection, blurring of image, removing noise, morphology, and edge detection. In blurring the image, the filter used is also known as smoothing kernel, mean filter, or low-pass filter. The simplest filter is spatial low-pass filter. Another filter used is the Gaussian filter, which is as shown. Both the 1D and 2D forms of the filter are given. Blurring is used to remove the identity or the other details in the image which we want to hide. The degree of blurring is equal to the size of the kernel. Focus your attention on the first image. Here we can see the cameraman, the camera, and the background very clearly and can identify the person taking the picture. But in the blurred image, we cannot identify the person. Blurring is one of the most popular used applications in the image processing systems. Template matching. In template matching, the filter is called a template or a mask. Template matching is used to find the object in the image. The brighter the value in the output image, the better is the match. What is sampling? A continuous function has to be converted into a sequence of discrete values before it can be processed in a computer. This is accomplished by using sampling and quantization. In simple manner, sampling can be understood as taking the values of the function at regular intervals, say delta t. This can be accomplished by using the impulse train function. When we multiply the impulse train by the original sample, we get the sampled values. The duration between the values depends upon the duration between the impulses in the impulse train. Figure A shows a continuous function. Figure B shows the train of impulses used to model the sampling process. Figure C shows the sample function formed as the product of A and B. And figure D shows the sample value obtained by integration and using the shifting property of the impulse. The mathematical form of sampling function is as given. The value of each sample is then given by the strength of the weighted impulse, which we obtain as shown as f of k into delta t, where k is any integer. Fourier transform of sample function. Let fu denote the Fourier transform of a continuous function ft. Thus, the Fourier transform of the sample function is as shown. The last line shows that the Fourier transform of the sample function is an infinite periodic sequence of the copies of f of u. The separation between the copies is determined by the 1 upon delta t. The sampling theorem can be summarized as a function f of t whose Fourier transform is 0 for values of frequencies outside a finite band from minus mu max to plus mu max about the origin, and it is called a band limited function. A lower value of 1 upon delta t would cause the period in sampled function to merge. Higher value would provide a clean separation between the periods. We can discover f of delta t from its sampled version if it can isolate a copy of fu from the periodic sequence by using inverse Fourier transform. This is only possible if the separation between the copies is sufficient. The sufficient separation is guaranteed if 1 upon 2 del t is greater than the maximum frequency. This equation indicates that a continuous band-limited function can be recovered completely from the set of its samples if the samples are acquired at a rate exceeding twice the highest frequency content of the function. This result is known as the sampling theorem. Here we use the term Nyquist rate, which is 2 times the maximum frequency. Thus, if we sample a function greater than the Nyquist rate, we can recover the original sample easily. The graphical result of the preceding summary is as shown. Based on the frequency used, we have 3 cases: oversampling, critical sampling, and undersampling. If we use frequency greater than the Nyquist rate, then we get oversampling. Here the distance between any 2 periods is sufficient enough to isolate one period and to get the inverse Fourier transform of this period. In the second case of critical sampling, the sampling rate is equal to the Nyquist rate. Here also we can get the original sample. Here the sampling rate is just enough to preserve f of u. Now what happens if we use the sampling rate less than the Nyquist rate? The result is the undersampling. In this case, we cannot isolate f of u. The net effect of lowering the sampling rate below the Nyquist rate is that the period overlaps and it becomes impossible to isolate a single period of the transform regardless of the filter used. The inverse transform would then yield a corrupted function of t. This effect caused by undersampling a function is known as frequency aliasing or simply aliasing. In words, aliasing is a process in which high frequency components of a continuous function masquerade as lower frequencies in the sampled function. Unfortunately, except for some specially, aliasing is always present in sampled signals because even if the original sample function is band limited, infinite frequency components are introduced the moment we limit the duration of the function, which we always have to do in practice. For example, suppose that we want to limit the duration of a band limited function f of t to an interval 0 to capital T. We can do this by multiplying f of t by the function h of t, which is a gate function. Hu has the frequency components extending from infinity. So, if the original transform of ft is band limited, convoluting it with Hu involves sliding one function across the other, which will yield a result with frequency components extending to infinity. As we cannot accept a sample function infinitely, aliasing is always present. There are two types of aliasing: spatial aliasing due to undersampling and temporal aliasing. It is related to the time intervals between images in a sequence of images. One of the most common examples of temporal aliasing is the wagon wheel effect, in which wheel with spokes in a sequence of images appear to be rotating backwards. But if you overlap the two images, we will figure that instead of moving backward, it is actually moving forward. The effects of aliasing are false identification and the formation of jaggies. In the figure A and B, the length of sides of the square are 16 and 6 pixels respectively. Here, no effect of false identification or say aliasing can be seen. But if we turn our attention to the figure C and D, we see that the size of the square are 0.9174 and 0.4798 respectively. In the figure C, we can see the effect of aliasing at the edges of the original image. But in the figure D, we can see the image as if it is the original image, but its actual size is 0.4798. Thus, it is the example of false identification. The second effect of aliasing is the formation of jaggies. Jaggies are stair-like lines that appear where there should be a smooth straight line or curve. For example, when a nominally straight unaliased line steps across one pixel, a dodge leg occurs halfway through the line, where it crosses the threshold from one pixel to the other. Through this example, we can better understand the effect of aliasing. The original function is given. The period p of sin pi t is 2 seconds and its frequency is 1 upon p or 1 upon 2 cycles per second. To recover this signal, sampling rate must be higher than 1 sample per second. The large dots are samples taken uniformly at a rate less than 1 sample per second. The sampled signals look like a sine wave, but its frequency is about 1/10 of the frequency of the original signal. This sample signal, having a frequency well below anything present in the original continuous function, is an example of aliasing. The effects of aliasing can be reduced by smoothing the input function to attenuate its higher frequencies. This process is called anti-aliasing, and it has to be done before the function is sampled. After all this process, now we want to recover back our original signal, that is, reconstruction from the sample data. This can be done easily if we succeed in extracting the single copy of the transform function and then taking the inverse Fourier transform of it. This can be done by multiplying the sequence by a low pass filter and then taking Fourier transform of this function, which is as shown. Between sample points, values of f of t are interpolated, formed by the sum of sin c function. Up till now, we have learned about the basic tools and techniques that are involved in determining Fourier transform of one continuous variable. Now, with the help of same tools along with the sampling theorem, we are going to determine the discrete Fourier transform of one variable. So what we are going to do is to obtain the discrete Fourier transform from the continuous transform of a sample function. In the previous section, we observed that the Fourier transform of a sampled band-limited function extending from minus infinite to plus infinite is a continuous periodic function that also extends from minus infinite to plus infinite. Here our objective is to derive discrete Fourier transform of a sample set with finite number of samples. The Fourier transform of sampled function is as shown. Before moving further, I would like to highlight the points that although fn is a discrete function, its Fourier transform fu is a continuous and infinitely periodic function with period 1 upon del t. And characterizing and sampling one period is the basis for DFT. Now coming back to our topic, suppose that we want to have m equally spaced samples of fu over the period u is equal to 0 to 1 by t. Then we will take the samples at the frequencies as shown. The expression which we get is the discrete Fourier transform which we are seeking for. Conversely, if the values of f of m are given, then we can recover the sample set fn by using the inverse discrete Fourier transform as given. The above two equations constitute a discrete Fourier transform pair. From this result, we observe that the forward and inverse Fourier transforms exist for any set of samples whose values are finite. The discrete Fourier transform pair is applicable to any finite set of discrete samples taken uniformly and is independent of the sampling interval or the frequency interval. It can also be shown that both the forward and inverse discrete transforms are infinitely periodic with the period m. Another tool of our interest is convolution, whose discrete equivalent is as given. The important result which this yields is that it gives one period of the periodic convolution. Therefore, the process is also referred to as circular convolution, and it is a direct result of the periodicity of the discrete Fourier transform and its inverse. Now let us determine the relationship between the sampling and the frequency intervals. If f of x consists of m samples of a function f of t taken delta t units apart, then the duration of the function is capital T is equal to m into delta t. In the discrete frequency domain, the corresponding spacing delta mu will be equal to 1 upon capital T. The entire frequency range spanned by the m components of the discrete Fourier transform is given by omega is equal to 1 upon delta t. Thus, we conclude that resolution in frequency of the discrete Fourier transform depends on the duration t over which the continuous function f of t is sampled. The range of frequencies spanned by the discrete Fourier transform depends on the sampling interval delta t. To better understand the working of discrete Fourier transform, let us take this example. Let us have 4 samples of a continuous function f of t whose sampled values are in the x domain. The given values in the x domain are f of 0 equal to 1, f of 1 equals to 2, f of 2 equals to 4, f of 3 equals to 4. Now we have to find the values of f of u from these values. Using the discrete Fourier transform and applying its formula, we use the values of the x domain in this formula. We get the values of f of 0 is equal to 11, f of 1 is equal to minus 3 plus 2j, f of 2 is equal to minus 1, f of 3 is equal to minus 3 plus 2j. If we were given the values of f of u and were asked to compute its inverse, then we would use the inverse discrete Fourier transform. In the x domain, f of 0 will be equal to summation of 11 minus 3 plus 2j minus 1 minus 3 minus 2j divided by 4, where 4 is the total number of samples equals to capital M. Thus, f of 0 is equals to 1. The other values of f of x can be obtained in the similar manner. We hope that this lecture has given you the better understanding of the topic. This lecture was presented by Kunal Kulshresht, Akansha Chaurasia, Ehtesham Kamali, Uddham Patel and Charmeet Kaur. Thank you.